A star dies, not quietly, not gently. In a single moment, it releases more energy than our sun will produce in its entire 10 billion year life. But when the explosion fades, when the light finally dims, something is left behind. Something small, something almost impossibly dense. And for decades, physicists have argued about what that something actually is. Because at the center of a dying star, the rules of physics as we know them may simply stop working. This is the question we are going to answer today. What actually lives inside the heart of a dead star? And the answer is stranger than almost anything else in the universe. Stars are, at their core, a balancing act. For millions, sometimes billions of years, a star holds itself together through two opposing forces. Gravity pulls everything inward. Nuclear fusion pushes everything outward. As long as there is fuel, the star survives. But fuel runs out. Every star eventually burns through its hydrogen. The most massive ones, stars 8 times heavier than our sun or more, then start burning helium, then carbon, then neon, silicon. Each new fuel buys a little more time. And then comes iron. Iron is where fusion stops paying off. You cannot squeeze energy out of fusing iron. So the core fills with iron ash, a sphere about the size of Earth, and it cannot burn it. It just sits there, growing heavier. In less than a second, literally under 1 second, the core collapses. It goes from the size of Earth to something roughly 20 kilometers across. That is smaller than most cities, and in that collapse, the outer layers of the star come crashing inward, and then violently bounce outward in a shockwave we call a supernova. The explosion is visible across entire galaxies. But we are not interested in the explosion. We are interested in what it leaves behind. What survives is called a neutron star. And to understand what it is, you need to understand what happens to matter when it is compressed that extremely. Normally, atoms are mostly empty space. If you scaled a hydrogen atom up to the size of a football stadium, the nucleus would be a marble at the center. The electron would be a speck somewhere in the stands. Everything else is void. In a neutron star, that space is gone. Gravity is so intense that electrons are forced into protons, creating neutrons. The entire object is essentially a giant atomic nucleus. A single teaspoon of neutron star material would weigh roughly 4 billion tons on Earth. 4 billion tons. In a teaspoon, that is more than the combined weight of every ship ever built by humanity. In a volume smaller than a sugar cube, and some of these neutron stars spin incredibly fast. We have detected neutron stars rotating over 700 times per second. 700 complete rotations. Every single second, they are called pulsars. And as they spin, they fire beams of radiation into space like a lighthouse, so precise, so regular that when astronomers first detected one in 1967, they genuinely considered the possibility that it was an alien signal. They were not wrong to be confused. Nothing in nature was supposed to be that precise. But it was not aliens. It was a dead star, a core of pure neutron matter, spinning in the dark. And that is not even the strangest part. If you could somehow stand on the surface of a neutron star, which you absolutely could not, you would be vaporized and then compressed into a thin sheet of exotic matter. But if you could, here is what you would find. A crust, made of iron nuclei arranged in a perfect crystalline lattice, compressed into a layer unlike anything on Earth. Below that crust, conditions change rapidly. The deeper you go, the stranger it gets. At a certain depth, the neutron density becomes so extreme that neutrons may start to do something unexpected. They may begin to flow without resistance, a state called superfluidity. Superfluidity on Earth exists only in laboratories, at temperatures near absolute zero. Inside a neutron star, it may exist at temperatures of 1,000,000 degrees or more. The rules work differently there. And then there is the core, the innermost region, where densities become so extreme that even our best physics, tested in the most powerful particle accelerators on Earth, cannot tell us with certainty what is happening. Here is the problem. Neutrons themselves are not fundamental particles. They are made of smaller things called quarks, held together by the strong nuclear force. Under ordinary conditions, quarks are always bound inside particles. They are never free. But some physicists believe that at the densities inside a neutron star core, the pressure becomes so extreme that neutrons themselves are crushed, and quarks may be freed, not confined inside particles, just roaming. A state of matter called quark matter. If that is true, the center of a neutron star contains a phase of matter that has not existed freely in our universe since the first microseconds after the Big Bang. Ancient matter, locked inside dead stars, still here. But some neutron stars are more massive than others, and at a certain point, a new threshold is crossed. If a neutron star is massive enough, the current estimate is roughly 2 to 3 times the mass of our Sun packed into that same 20-kilometer sphere. Not even neutron pressure can hold back gravity any longer, and the star collapses further, past the neutron star, past quark matter if it exists, down to a point where space-time itself curves completely closed. A black hole. At the center of a black hole lies what physicists call a singularity, a point or region where density becomes theoretically infinite and our equations produce nonsense. Not large numbers, not very small numbers. Nonsense, division by zero. The math breaks. This is not a metaphor. General relativity, which predicts black holes in the first place, also predicts its own failure at the singularity. We genuinely do not know what is there. Some physicists think quantum gravity, a theory we have not yet completed, will eventually describe it. Others think the singularity is a sign that something more fundamental is happening. That space and time as we experience them simply do not exist at that point. We are not just guessing at this. In 2017, for the first time, we detected 2 neutron stars spiraling into each other and colliding. The event sent ripples through space-time itself, gravitational waves, detected simultaneously with a burst of light across the globe. That single event told us more about neutron star interiors than decades of theory. And we are building better detectors, better telescopes, new tools. The question of what lives inside a dead star is not just an abstract physics puzzle. It is a question about the fundamental nature of matter itself, about what the universe is made of at the deepest level, about whether the rules we know are the only rules there are. Because here is the thing. Every atom of iron in your blood, every calcium atom in your bones, was forged inside a star that later exploded. You are, in a very real sense, made of stellar remnants. The dead star is not some distant alien object, it is part of your story. So, what lives inside the eye of a dying star? It depends on the star. For most massive ones, it is a neutron star, an object 20 kilometers across, spinning hundreds of times per second, containing matter so dense that a teaspoon outweighs a mountain range. Matter that may be superfluid, matter that may contain freely roaming quarks last seen in the first moments after the Big Bang. And for the most massive ones, the ones where even neutron pressure is not enough, it is a black hole, a region where space-time curves completely closed, where our best equations stop making sense, and where the answer to the question may require an entirely new theory of physics that we have not yet written. We know it is in there. We just do not yet have the language to describe it. And that, honestly, is one of the most exciting things I can imagine. Not knowing, but knowing that we are getting closer. If this kind of question keeps you up at night the way it keeps me up, subscribe, because next time we are going to look at something equally strange, the moment just before the Big Bang, and whether the concept of before even means anything at all. That one will change how you think about time itself.